Hey everybody, welcome to the distributed SQL cast demo session. Today we're going to do a really interesting deployment. We're going to deploy a Yugabyte instance of our database across 3 separate clouds. And then we're going to run a containerized application for an e-commerce app that runs in front of Yugabyte. And we're going to see some scenarios around how that workload is distributed. And then finally, we'll take a look at some performance numbers and sum up how the system behaves from a performance and resilience perspective. So I've got this diagram on my screen. I just want to quickly walk you through it. When we're deploying this app, we actually have the demo, which is a Kubernetes demo on our GitHub repository. If you go to github.com/castai, under the examples repo, you'll see a boutique web shop with Yugabyte. And that'll provide you all the assets you need to deploy this demo in your own environment or in your own CAS cluster. So let's take a look at the diagram and walk through that very quickly. So what we're gonna have end user facing or internet facing application that is actually distributed across 3 clouds. We're gonna use AWS, we're going to use Google, and we're going to, for fun, normally we would use Azure, but for fun in this demo, we're going to use DigitalOcean as our 3rd cloud for disaster recovery and throughput. So we're going to have exposed load balancers and ingress controllers in each one of these 3 clouds, and then that's going to be orchestrated using a DNS resolver, an authoritative DNS resolver that's going to load balance traffic to all 3 clouds. Inside the clouds, we'll have Kubernetes running in a highly available mode. And we'll walk through how we configure that with Cast. And then we're going to have deploy our e-commerce application in all 3 clouds. And we're going to wire that application up to use Yugabyte. And in this case, we're going to use the Redis flavor of Yugabyte as the application uses Redis for its shopping cart app. So let's go ahead and get started. We'll start with all of the infrastructure, and then within the next 20 or so minutes, we will have built up the entire application. Okay, so we're going to start on the cast console, and we could have done this through Terraform or through API, but we're just going to use the console because it's nice and visual for this demo. And so the cast console, when you log on, you'll see a list of your clusters that you may have created previously and some instructions on getting started. We're gonna start by creating a cluster here, and then we're gonna show you how to make it a multi-cloud cluster. And so unlike other multi-cloud paradigms, this isn't a federated approach. So it's not like we have 3 separate Kubernetes clusters that are kind of talking to one another. This is one cluster that's connected together through a virtual multi-cloud private network. And so Cast orchestrates that on your behalf. So to get started, it's really simple. We're gonna use a Cast Yugabyte demo 3 as our cluster name, and then you have to pick a region. So I'm in US East, so let's use the US East region to make things easy. And then we're gonna choose a cluster configuration of highly available. And if we go back to our demo, you're gonna see that's gonna basically create 3 master nodes, 1 in each of the cloud, and they're going to be connected together through a distributed etcd database. And that's what's going to give the Kubernetes control plane its high availability and redundancy. The last thing we need to do in order to start the cluster creation process is we want to select the clouds that we're going to use for this cluster. So we said we were going to use AWS, and that's great. We're also going to use DigitalOcean. And the last one we said is we were going to use Google. Now you'll notice that I've already pre-created a set of cloud credentials here. But the way you would add a cloud credential here, for example, if you wanted to add a Google cloud credential, you would follow the instructions here in the onboarding for cloud credentials, which would end up producing a service account JSON file. You would paste it in or read from file here. And then the Cast platform would validate that those credentials have all the right permissions, IAM permissions, in order to do the work that's required. So let's go ahead and hit create cluster. The system will start creating resources such as networks and load balancers and virtual machines, and basically everything you need in order to create a multi-cloud environment. It's going to take about 10 minutes to create. We're going to kind of pause the demo here just for a second while this creation process kicks in. And then we'll start with the ready cluster that is deployable. And so we'll see you back just in a second as this cluster finishes up. Excellent. So now we have our ready demo cluster. And you can see that it is stretched across AWS, Google, and DigitalOcean. And actually, if we'll just quickly log into one of these cloud consoles so that we can see how it looks. You'll see all of the events here in the cluster activities screen that shows how the cluster is created. And you'll see that we've populated the cluster with several different nodes. So we've got our master nodes here at the top of the list here, and then we've got a bunch of worker nodes. And we're going to use the large worker nodes in this list to deploy Yugabyte. So that's going to come in just a second. But before we go to the deployment phase, let's take a look at what you would see from a IaaS or a cloud service provider perspective. So if we go into DigitalOcean and I'm logged into account, you would see I have virtual machines for demo 3 and demo 2 that represent my my nodes, both my master and my worker nodes. And similarly, I have, if you look at instances on AWS, we'll see a bunch of instances created that are running our demo cluster environments. Excellent. So let's go ahead as the next step and let's deploy Yugabyte as we have the instructions in the examples. So I've got a deploy script and I'm just going to pull it up here. And so in this deploy script, what are we going to do? We're going to create a Kubernetes namespace for AWS, for GCP, DigitalOcean, and we're going to create a namespace for our boutique app. We're then going to go ahead and apply each of the YAML files for each of the cloud providers. And this is a deployment YAML file that was created from the Helm chart, from Helm as input. And then we're going to wait for these master nodes to become ready. And this should take about 5 to 10 seconds for the Yugabyte masters to become ready. And then finally, I've commented these sections out because we're going to take it step by step. We're going to create a Redis table. Here, we're going to use this setup Redis table command, and we're going to exec into one of the pods in order to do that. So let's go ahead and get started on that. Here we go. We're going to run our deploy.sh file. But just before we do, so I'm going to go ahead and kick it off because it's going to start creating the namespaces. But one of the things that you'll notice in the cast cluster environment is that we've got this Kubernetes UI that's automatically pre-built and pre-authenticated for you as a cast user. So when we look at our namespaces in the K8s UI, you'll see all of those Yugabyte. There's a bunch of namespaces, but you'll see the Yugabyte namespaces and the boutique app namespace created. And if we actually go to deployments here, and we look at let's take a look at Yugabyte DO or DigitalOcean, for example. You see now that we just deployed the master nodes about 30 seconds ago. If we look at AWS, that may not exactly be ready. Oh, that's ready as well. And maybe Google just for completeness. Okay, and you'll also notice that there are stateful sets, and those stateful sets are bound to, if we actually open them, they're actually bound to persistent volume claims. So there are storage class, so CAS provides a storage class for each cloud, and it's block storage for AWS, DigitalOcean, and Google in our case. And each of these storage classes are used for the persistent volume claims we create. So great, now we've got the foundation of our Yugabyte deployment inside of our Kubernetes CAS cluster in just a few minutes. Let's take a look. It looks like all of those resources are set up and all of our pods are running for the Yugabyte masters. Excellent. So now the last thing we need to do is let's go ahead and create this Redis setup. And then we're going to actually, you know what, let's do the port forward first. So in the README file, you'll find a little bit of a tip on how to do port forwarding to the Yugabyte master. So let's go ahead and do that. We'll do that in a separate window. And that should allow us to use the Yugabyte UI from our local computer. So we don't have to expose that Yugabyte administrative interface to the internet, right? And so we can just pull that up on localhost 7000. Here we go. And we should see Yugabyte deployment successfully created. And you'll see that there are three servers running. 2 are followers and 1 is a master. So the master happens to be in AWS, US East 1. The 2 followers, 1 is in Google and 1 is in DigitalOcean. So we've got our network set up, we've got our infrastructure set up, and we've got Yugabyte up and running. So let's go ahead and enable Redis, and that's going to give us the pieces we need for our application to run successfully. So we're going to just go back to our deployment file. I'm going to copy this kubectl command, and let's run that one and set up Redis for ourselves. Excellent. Now, if we go back to the Yugabyte user interface and we actually look at all of the tables that are created, 1 second here. One of the things that you should see is if we search for Redis, you will see a system Redis table, and then it's actually up and running. And if you click on it, you'll see the details in terms of the tablet. Excellent. So we've got our application is all primed and ready to run on Yugabyte. Let's now go ahead and deploy our e-commerce application, and I'll just walk you through a couple of areas of that app so that we preset it up to work correctly. Because remember, we're going to expose this app to the internet for high availability. All right, guys, so let's go ahead and deploy the app. But before we actually deploy the app, we know we're going to expose this to the internet. So I want to introduce you to a couple of concepts. One is the GSLB DNS name. So you'll notice on your cast cluster in the console, you'll see there's this entry here for a DNS name. And if we actually copy it to clipboard and we open it up in the browser, you'll see that it'll be an Nginx 404 error, meaning there's really no host name and no ingress to listen to this DNS name. So it's pointing to the cluster, but it's not successfully resolving to the name. So I'm going to show you how to deploy as part of this whole cycle. We're going to deploy a TLS certificate very quickly, and we're going to also watch this resolve into a real app. So let's just copy this into clipboard, and I'm going to show you in the deployment file a couple of really interesting things that you should know about the cast cluster and the deployment in general. When we're deploying this app, it's made up of multiple microservices, right? So there's a front end, there's a recommendation service, there's a shopping cart service, and then there's the thing that is required to talk to Redis. And so we're gonna look at that in this deployment. But the first thing I want to show you here is the front end container, which is actually responsible for rendering the e-commerce site, has some interesting properties. So the first property it has is it has a replica of 3. And what we've purposefully done here is we've replicated this pod and others to be in multiple clouds simultaneously. So the microservice actually exists in DigitalOcean, Google, and AWS. And we do that through node affinity or any affinity, and that's done through a node label. So for every node that's created in a cloud service provider as a virtual machine, that node is labeled with one value of AWS, GCP, or Azure in the case when you're using Microsoft. So that's cool. The next thing I want to show you is kind of the Redis configuration, because this demo was originally designed to run with just a small Redis pod. But in our case, we're actually using Yugabyte's implementation of Redis or Gedis. And so what we have to do is we have to put in the Redis addresses, and we're using the core DNS name to resolve to those. So here we've got our three servers that are listed out, comma separated, and including the Redis port here. So you'll see that. So we passed those 3 things for AWS, DigitalOcean, and that way the shopping cart app, or the cart service in this particular case, knows where to find its highly available Redis instance. Cool. The last thing I want to show you in this deployment file before we go ahead and deploy it is the is the ingress controller. So we've developed this sample to use Let's Encrypt, and Nginx is an ingress controller is installed by CAST by default. What we have to do is we have to provide a host name. So in this particular case, I'm using shop-yb.verticacloud.com. It's just a dummy domain name that we own. And we have to really configure this DNS in order for it to work. So we're going to just really quickly do that. We're going to go ahead. Remember, this is the DNS name that I pulled that currently resolves to nothing. And we're going to open up our DNS provider. In this particular case, I'm actually using DigitalOcean for that purpose. So we go into networking. We're going to go into domains, verticacloud.com, cool. And we're just going to create a very simple CNAME here. So we're going to create a simple CNAME record. It's going to point to this. Well, we got to get rid of the HTTP. That's certainly not going to work. And then we're going to give it a target host name. So I obviously have forgotten what it is already. It's shop.yb. Cool. It's always better to cut and paste. And so now we have shop.yb.verticacloud.com pointing to this DNS record. Let's go ahead and create this. And then what that's going to do, let's go back to our diagram for a second. What's that going to do in our configuration is it's going to provide the global load balancing that we have up front. So when an end user hits that DNS name, it's going to hit either one of these 3 load balancers that are provisioned in one of the clouds, go through the app stack, obviously go to the data store, and then return with a result. So that's pretty cool. We've set that up with that CNAME entry. We should see that. Let's go ahead and copy this in, and we can replace it. We still won't have an answer here, but at least this is the domain that we're going to use. And we know that it's resolving because we got an answer from the server, although we still don't have a certificate deployed. So I think we're all ready now. Let's go ahead and deploy this YAML file, and we should see the services come up. Okay, we're going to deploy to the boutique YAML file to our boutique namespace. Let's go ahead and do that. And now if we look at the Kubernetes UI here, under the boutique namespace, we'll start to see all of these services deploy. We have an advertising service and a shipping service. The card service, this is the card service that actually talks to Redis. And we'll slowly start to see all of those pods deploy in just under 60 seconds. So great, now we've got, if we go back to our deployment diagram, we've got our Yugabyte instances deployed. We know that one in AWS is the leader, and then we've got 2 followers. We've got obviously our Kubernetes infrastructure deployed, and now we're deploying the application that's actually going to speak to the Yugabyte instances over the Redis protocol. So something like this. So if we go back to the Kubernetes dashboard, we'll see all of our pods have been deployed. Excellent. And now remember, we had the eShop URL that we pointed in DNS. Theoretically, this should all be working and talking to Yugabyte as database. So let's take a look and let's refresh the page here. And sure enough, we see our e-commerce app come up. In this particular case, we've added a banner so that you can see which cloud is actually rendering the front end of the application. So in this case, it's Google, but if we actually refresh, we'll see DigitalOcean pop up and then AWS pop up. Remember, in that DNS round robin format, the persistence piece is really important because remember, we want the persistence to be highly available regardless of cloud failure, regardless if AWS goes down or Google goes down. We want our application to remain up and resilient. So if we add to cart here, we'll see our camera added to the shopping cart. In this particular case, the cart page was displayed on DigitalOcean. But if we refresh, we'll see that same shopping cart with the same exact content being refreshed from different clouds with complete persistence using a multi-cloud database, right? So once again, the data store here is this Redis table that's where the current master or the current leader is in AWS US East 1. And the the followers are in the other cloud, but the data is completely consistent using Redis protocol across all 3 clouds. And one of the things I want to show you just before we move on to the high availability and the performance topics is just a leader into performance, which is the latency of the system. So one of the key things we at Cast, when we pair clouds together, we like to pair them together in what we call a Goldilocks region. And what that means is that latency should be no more than 10 millisecond in the worst case from cloud to cloud. So one of the interesting things here that if we actually go to all namespaces, we'll open up our Cilium CNI network driver here. So there are pods deployed here for Cilium, and we can actually deploy exec into one of those pods. And I just want to give you a quick perspective of latency between nodes. So we can do Cilium health status, and that'll give us a snapshot of latencies between all of the clouds, right? So here we see somewhere between 2 to 3 milliseconds, in the worst case, 6 to 8 milliseconds. So we have amazing connectivity. And this is achieved, again, through that virtual multi-cloud private network that we've been able to create between all of the nodes in the Kubernetes fabric to achieve a secure private network that's extremely performant. Okay, one of the things we wanted to show from a high availability perspective is what happens when one of the database nodes disappears. Like, how does the application behave? How does the database system behave in general, right? So without having to restart or rebuild a bunch of components of the app, how do we simulate? So we're going to simulate the failure here just by killing the pods or maybe the stateful sets, and then see what happens to the environment, both from a Yugabyte perspective, and then we'll look at the application as well, right? So we're going to delete the stateful set here. We're going to delete the stateful set here. And then if we refresh the user interface, we see that in AWS, we now have a role for the master, the previous master, or the previous leader that is now unknown because we've obviously killed these guys. And now Google has become the leader in a completely different air zone, in a completely different cloud, right? So now we've got a situation where we have one leader, one follower, and we have one of these nodes which is unresponsive, obviously because we've killed it. So what happens when we look at our application? So we can see that if we refresh the browser, we can see that our cart has maintained complete consistency, even though we lost our leader. And so if we go back to the Yugabyte UI, we'll see, okay, like we've lost our leader here, and we now have a new leader in GCP, but we maintained complete consistency, and the application was able to fail over to our new leader and continue to work. So we can, in fact, let's give this a try. We can add additional items to the cart in a write mode, and we see that we have continued consistency even through failure. All right, guys, one of the last topics we wanted to cover is some performance benchmarks for our multi-cloud Yugabyte setup. So I'm just going to walk you through what we did to set up the benchmarks and then some interesting results that we got out of our multi-cloud setup. So first of all, we used TPCC benchmark. And so for those in the database kind of world, you'll probably be familiar with this online transaction processing benchmark. But if you think about it, it's kind of like an e-commerce app, which is very similar to the e-commerce app that we've done earlier, that uses a lot of interesting transactions around payments and order status and order details and shipping, et cetera. So this is a highly parallelized test suite, but it's also very standard. So when you get metrics that come out of a TPCC benchmark, it's very easy to kind of compare solutions, right? So let's take a look at how we set this up. The first thing we did was we set up a mono cloud or a single cloud version of Yugabyte on the recommended infrastructure or hardware. So we created a GKE cluster in US East 1, and we used N1 standard 8, which we provisioned three total VMs, one in each availability zone. So it kind of mimicked the 3 availability zone cluster. We also ran, each VM ran a Yugabyte master pod and a table server pod, and each of these requires 2 CPUs, 2 gigs of RAM, and 4 gigs of RAM respectively. So that fit really nicely into the overall provisioned hardware that we provided for GK8. Next, we set up, so we're going to look at the results for the monocloud. So next, we set up a scenario A multi-cloud, and that's 3 clouds clustered using a cast cluster that spans AWS, GCP, and Azure. We networked together the 3 clouds using VPN services from each cloud provider, 2 tunnels per cloud pair. We use that for high availability, and then these are the instance types that we used. We used the N1 standard 8 in GCP, M5 2x large in AWS, and standard D4 V2 in Azure. The pod specs all remain the same. And then we had 2 more multi-cloud scenarios that we looked at. So multi-cloud scenario B was we created 2 clouds, a cluster with 2 clouds, AWS and GCP, same networking through VPN service providers, same instance types, but we doubled up the instances in GCP because we needed at least 3 replicas for Yugabyte. So 2 were in Google, 1 in AWS. And in the last scenario, which is scenario C, we also used 2 clouds. The only difference between scenario B and scenario C was that we used node-to-node full mesh WireGuard VPN as opposed to the cloud services VPN. And we saw some difference between those, but let's take, when we dive into the results, you'll see some of the differences here. Cool. So again, using this multi-cloud scenario with Yugabyte in each availability zone or each cloud, in the cases of scenarios A, B, and C, let's take a look at what we were able to achieve. So the 2 core kind of high-level metrics that the benchmark looks for is transactions per minute. So the GKE baseline was 128.13 transactions per minute. 3 clouds was 126 transactions per minute, and then B and C were 127 transactions per minute. I would say that result is almost negligible in terms of difference between single cloud, multi-cloud, or multi-cloud with different VPN types. So we almost saw no throughput difference between these scenarios, which is great news because it shows that we can create a highly scalable, highly available cluster in various clouds that actually performs really well. Also, the efficiency metric shows the same thing, with the GKE multi-zone baseline being 99.64, and then 2 clouds being 99.51 and 98.98. So I would almost call these statistically insignificant differences in that row. What's interesting is the additional latency we saw in some of the write-intensive operations. So for example, when you're creating a new order in Google, we saw average millisecond latency. So these are averages now, 51.48 milliseconds. Across 3 clouds, we saw 121 milliseconds, which is significantly higher. And across 2 clouds, we saw 71 milliseconds. So this is where we see a write to one of these clouds, most likely, and this is without understanding all the details of the Yugabyte architecture, we probably have extremely fast reads from our local storage, but when we write, we have to synchronize with the leader, and that takes multi-cloud communication. Now, in an average, and this is why I think the transactions per minute and the efficiencies were so good here, because in an average e-commerce application or almost any other application, you're going to have a very healthy mix of reads versus writes. So most of your application is going to be very read intensive, and there's going to be some write. So we kind of think about the 80-20 rule when we split reads and writes. So take a look, just to kind of highlight that point. We saw the payment service average, which is 36 milliseconds here on baseline, about 47 milliseconds here in this kind of 2 cloud We'll call this the scenario B is kind of our most optimal scenario. But take a look at the order status results. So in GKE, because we're only reading from the order status table, we're only seeing latency of about 18 milliseconds for reads. But take a look at the 2-cloud cluster. We actually saw a lower average read time for a multi-cloud cluster. And again, I think that's because when we're reading through these pipelines, we can, one, read through them in parallel, and also there's no cross-cloud communication required. So, and just below, this is the same table of information. It's just highlighted in graphical format. One of the things that we want to look at next is and we didn't have a chance to benchmark this fully with the Yugabyte use case, is what happens when we implement layer 2 direct connect in our network topology. So rather than using VPN, what if we were to use the fiber connection between clouds, which is available through Equinix or Megaport, other such networking providers? So that's something that we're going to reserve for kind of future experimentation and benchmarking. Stay tuned for those. But for now, I hope you've enjoyed the high availability, deployment, as well as the benchmarking portions of our demos. Thank you very much, guys, and looking forward to chatting very soon.